Hi everyone. I hope you had a good session so far. So we are going to talk about, our challenge for the posters. So how is it going? Okay, perfect. So for the posters, we have received 135 posters in total. And as you know, we had two tracks, one feedback track that for students who wanted to receive some feedbacks for, I would say, for the research that they are working on. And we had 83 posters who were assigned for the ranking track. And we had, originally we had scheduled like 2 sessions for the posters on Monday and Tuesday. And we had a very, I would say, nice poster session. Thank you all for participating as poster presenters, as like participants, and also researchers who were involved. So for the review process, we tried to do some, I would say, semantic matching for the posters topics and like the, I would say, judges to ensure that, experts would review your posters. And the evaluation was on several criteria, unlike the motivation, on the soundness of the method, the experimental setup and the data evaluation, and the impact in the MENA region, and also, I would say, the communication. And as you may observe, we noticed that we need to extend our evaluation process for 2 more sessions to ensure that all of you would receive at least 2 judges, because some of our I would say judges couldn't make to come here, and so basically the availabilities were dynamic. So we tried to ensure that all posters, they would receive at least 2 or more judges. In total, we had 42 judges. Let's thank them all. Who contributed to 175 judgments in total. And at the end, we tried to normalize the scores, basically based on, because of course, some of the judges, they are more generous than the others in scoring, or more, yeah. And then also based on, I would say, the scores and also nominations that we had, we tried to select, I would say, the top 3 final presenters. So we start from the 3rd one, the I would say, last winner. So we have Mohammed Bayan. Yes, please. If you want to present together with, yes. The poster title is Reasoning with Vision Language Models for Meme Understanding via GPRO. Yes.
It's not the most of this version, so we will figure it out.
Yeah, sure.
Yeah, hello. So my name is Mohammed Bayan. I'm a master's student at Qatar University, and I work as a research assistant at QCRI in the ALT team. And my colleague, Ali Shahrour, he is also working with me at QCRI. Yeah, so in our research, we focus on detecting hateful memes. Okay, yeah. Yeah, so memes are complex. They consist of visual, textual, and cultural nuances, which make them hard to detect. And most of the systems do not focus on explainability, or they focus on the direct explanations, the direct classification as hateful or not. not many systems focused on the fine-grained analysis of memes. So in this work, we focus on how to build a system which is like which can think as an annotator. So when we build a data set, we write the guidelines which contains fine-grained, let's say, labels for each class. And they think like why it is hateful and why it's not. So here we have like two here we have like don't think it's here, two fine-grained labels for hateful and one for not hateful. We label the hateful memes as for the attack type, which can be like stereotyping like this, and the protected category, which can be like a nationality, based on the gender, the color, and etc. So in our system here, we first prepared the data set. We used GPT to generate a chain of thoughts based on the content of the meme plus the fine-grained analysis. So why are we using GPT to generate a chain of thoughts? We tried to evaluate multiple open source and closed source multimodal LLMs, and it turned out chain of thought and thinking, like for models like Kimi and Quen, it hasn't improved much. So we are trying to improve the thinking capabilities of these models. It is the first stage, the SFT stage. The second stage is the RL or GRPO stage, which improve the model's thinking. We have the reward function here. It consists of 4 parts: the accuracy of the label, the meteor score, which is like a very simple lexical similarity score, easy to compute, very cheap, to compute the how good the rationals are. And we have the format, like for the model to force our format here, and the length. So we added a length reward here to penalize shorter thinking, because we tried to run multiple experiments, and it turned out the model will collapse, the thinking becomes shorter and shorter, and they become like semantically empty. So this term adds more like stability to the training. Yeah. So here are the results. So the top 3 rows are the SFT results. So the first one is classification only, like direct classification as hateful or not. Second one is classification plus fine-grained. So we added the fine-grained data set to the training set and evaluated on the binary data. It improves a little bit. The third one is with GPT-generated chain of thoughts. Yeah. So it improves, but we wanted to improve further. So we started from each checkpoint with GRPO training on our objective, and the best result is the last one, which started from GPT-generated data. Yeah. So here are the comparison with the state of the art. So the last one is our system. It got accepted in the web conference like last week, and the one MenaML, it is like mainly the data set. It is also our work. It got accepted in MLP 2025. Yeah, so we can see that our system surpassed the state of the art. Yeah, yeah, and that's it. Do you have any questions?
Okay, and now we have our second winner. So actually, like for the second place, we had a tie. And the second prize go to...
Hello, everybody. So I need you to say is whenever I say the winner is. Are you good? Are you good? You say is whenever I say the second winner is. Okay? So the second winner is, the second winner is, the second winner is...
Syed Talal Wassim.
All right. So am I audible? Okay, all right. So, so basically, my colleague Hamid and I, we work at the University of Bonn, and these are basically two projects that we presented here. This one is at ICCV 2025 last year, and the one next is at CVPR 2025. So in this paper, what we are looking at is the problem of action anticipation, and particularly we're looking at dense action anticipation. So what we are focusing on is like, we have some video, some super long video, maybe up to 30 minutes long, and we want to do is that given, let's say, only a visible area of, let's say, 10% of that video, we want to be able to say what happens and exactly when it happens in the remaining part of the video. So let's say if you look at the results at the top, what you want to essentially say is like before the red line is what you can see of the video, and you want to predict the future and exactly the timestamps of what actions happen at which time in the future. And the way we build this system is that we have some features from the past that we have observed, and then we add zeros because we have no observation of the future, and then we basically build a diffusion process around this. So we add noise, and then we do a denoising system to predict our final frame labels. Now, how do we build this architecture? We use what's called a Mamba architecture. Now, typically for denoising decoders right now in literature, you use a lot of transformer architectures. Now, the problem with anticipation is that you have super long videos. You have token sequences that can go up to like 500,000 in some cases. So you really cannot do transformers on a limited amount of compute. So what you do is what's called a Mamba-based architecture. Mamba is based on the old state space models with a slight modification where in the state space equation, you have your current hidden state at time t as a function of the previous hidden state at time t minus 1, and with addition with a input at time t. Now, the input gate B and the output gate C and the time step delta, they are all input dependent. However, the matrix A, which controls how much you remember of your past, that's fixed in Mamba. And the problem with that is like, no matter what your input is, if your A matrix is fixed, then you're essentially saying that I'm going to remember the same amount of past no matter what kind of video I'm looking at. And that's fundamentally very problematic. So how do we solve that problem? Is that we go to a mixture of experts approach, but we don't do mixtures in a very typical way. In typical transformer architectures, mixtures are done by simply taking a transformer block, you take your MLP, and you replicate your MLPs to build your mixture. Instead, over here, we take the A matrix and we make a pool of A matrices, and each time an instance comes in, it chooses the right A matrix for itself, which essentially then allows the model to modulate how much of the past it remembers depending on the kind of input it receives. So it's very simple. The original Mamba unit had a simple static A matrix, and for this one, we have like multiple A matrices, and some router, dependent on the input, selects the right A matrix. Now, it's a very simple solution, and it actually adds only like 5% extra parameters, maybe 10% extra compute cost. But the results are quite shocking. So when the model is being trained, it's basically, if you have a long procedural video, let's say, of cooking some kind of dish or fixing a bicycle or something, you don't really see during training what the overall activity is. So the model doesn't know that the activity is cooking something, or I don't know, making coffee or making tea. It doesn't actually know those activities. What the model only sees is you pouring water, putting a pan on the stove, or something like that. But we get some very interesting results. What we plot over here is, because we have a mixture, we can actually check which A matrix is being selected by the model. So these A matrices that we have here, so for example, video A, it chooses the first one in the first block, the first one in the second block, the second one in the third block. So we can actually plot a matrix of which A matrix is being selected. And if you build a TSNE of that, and we color by the overall categories that the model did not see during training, we get close to perfect segmentation. And not only that, if you notice, you have activities that are very similar. You also see them close by. So you have, let's say, heating milk, or making tea, or making coffee. You see them clustered very close to each other. But salad, which has nothing to do with making coffee or making tea, is on the other end of the plot. So not only do we get perfect segmentation, we also get these very emerging properties from not actually training on any of these classes. And that's like the core takeaway. Of course, I can talk about we achieve state-of-the-art results. We pretty much beat every data set out there on this project. But the idea is that we achieve this very interesting emerging property and this emerging trend where just the selection of the A matrix by the different instances at test time actually indicate what the overarching activity is. So you get like a secondary result from the network just by observing the path the instance takes through the network. And that's the key takeaway that we want to really push over here. And yeah, that's kind of the quick summary of the work. I don't think I should take more time. So yeah, that's all.
So basically, the tie that we had among two colleagues, Hamid and Syed Talal, I think there was a confusion that the order was a bit. So basically, so this work was the joint work of Hamid Suleman and also Syed Talal Wassim, and the so I guess the second one we already revealed. Yes. So basically, if you could also, for the second project, if you could
Okay.
present it would be great.
All right, so all right, so for this project, what we were focusing on, so this is from CVPR 2025 last year, and we were looking at video language models. And particularly with the problem that we were looking at is the problem kind of emerges of us analyzing open source work for inconsistency, honestly, in scientific method in somewhat. Basically, if you look at open source literature on video language models, or even vision language models in general, you'll see each new paper comes out and it claims that it achieves state-of-the-art results. It's the best in all of its competitors, which is, I mean, true. But the thing is, if you look at the paper, what are they changing that achieves those state-of-the-art results? And you'll find that they change the vision encoder, they change the amount of data that they train on, they change the LLM, or they change even the training strategy. So everything's changed. So then the question becomes where are those improvements even coming from, right? Because scientific method says that if I want to know the impact of some variable, I have to keep every other variable constant. That's the only way I can know the impact of that particular variable. And we don't really see that consistency or that evaluation in a lot of recent open source works. So what we tried to analyze was what is the contribution or the impact of the vision encoders in these so-called vision language or video language models. So we took a very bad LLM, bad by today's standards, Llama 2, and we put every single vision encoder that we had available at the time behind it, and we trained on a standard fixed data set. And we found out that the amount of impact that it takes by changing the vision encoder, keeping the parameters approximately constant, is hardly around 0.5%. Maybe 1% in some data sets, but rarely it's 0.5%. So that brings the question that what are the vision encoders even contributing? Because the vision encoders can be as big as 1 billion parameters. So what are those 1 billion parameters even doing if the difference doesn't really mean too much, right? So and if you look at the structure of vision language or video language models, at least in the open source community, you pretty much see that most of them work you have a video encoder, you have some combination of image or video encoders, you put some MLP on top, and you then have the LLM, and you fine-tune the LLM and the MLP. And it makes a lot of sense why different video encoders or vision encoders don't really make a difference, because what you're essentially doing is you're also doing self-attention on the visual token inside the LLM. And because you're fine-tuning this very large 7 billion, 14 billion parameter LLM at the end of the day, you are essentially doing self-attention between the tokens. So you're basically solving the vision problem inside the LLM as well. So no matter which vision encoder you use, eventually the LLM kind of converges to an alignment with that vision encoder. It kind of converges to a similar result. So it's basically the LLM putting up with at least solving the image problem. So our thought process was that, OK, then we don't really need the vision encoder. Instead, what we should do is try to cover up for the LLM in something that it does not have, which is explicit temporal modeling. So we replaced these heavy vision encoders with just 45 million parameters, specifically for temporal modeling. And in terms of performance, that reduces your vision size from 300, 400, 1 billion parameters down to 45 million. Your flops go down by about 80x, and you increase latency about 5, 6x. And in terms of results, so the x-axis over here is in log scale, and the y-axis is accuracy on one particular data set. And you can see when you train on the same amount of data, again, like this thing about different papers training on different data and then claiming improved results. When you train on the same amount of data, with only 45 million parameters on the vision encoder, we are able to equal or beat pretty much every other model that trains on the same data, and the only ones that are better than us use orders of magnitude more data. And that's the key takeaway. So by just using 45 million parameters, that's like shorter than even like a VIT-based that it normally use in most like standard projects, we are able to equal these very large architectures. And how do we actually achieve that? So the way we do this is we start, like our philosophy is the LLM is able to solve the image problem somewhat. So we want to basically do temporal modeling outside the LLM. And that's what we focus on. So we take our video, we create patches, the standard patch embedding, and then we do localized temporal modeling. How do we do that? Standard stack of convolutions. Okay? So we do a stack of convolutions, temporal convolutions to model local temporal information, and then we add a dynamic position encoding, which is quite common in a lot of video models today. After that, we have our per frame tokens, with some localized temporal aggregation. We also make an observation that although attention is quite expensive, if your number of queries in your attention operation is 1, then attention becomes a linear operation. And we want to take advantage of this fact. So what we do is we define a single query at top, and we take all our frame tokens and extract keys and values from the frame tokens. A single learnable query summarizes the entire video tokens into one single global representation. And we keep that aside for a minute. Then we take our per frame tokens again, and we realize that there's a lot of spatial redundancy in videos. So we want to reduce that redundancy, but if we reduce that through some max pooling or average pooling, then we kill a lot of important signal. So again, we take advantage of the single query linear attention. We again define one single query. Keys and values come from the 2x2 window that we want to reduce, and we again do a single attention block. And we are able to reduce the token down to just 1. So the overall number of tokens is reduced by 4. Then again, we also want to model per frame information, because if you have some fine-grained questioning, you want to really know what's the content of each individual frame. Again, we do the same thing. We take one single query and each frame's tokens, again do a single attention block. The attention is now again linear, and then we again calculate per frame tokens through this single attention. And then we merge the global information that we calculated earlier into these individual per frame tokens. And that's pretty much the overall operations. We then do a linear projection on these per frame tokens, add back in our reduced special tokens, and add some demarcation about where one row of the token starts and one row of the other row ends. And that's pretty much it. We add an MLP, fine-tune with the LLM, 45 million parameters, beat the state of the art, or equal them on the same amount of training data. And that's the key takeaway here, that maybe like for video language models, what we need to do is better design choices rather than just simply increasing data or using bigger vision or video encoders. And essentially, we need consistent, proper scientific methodology when we are doing evaluation. We can't just claim state-of-the-art results by like increasing 3 or 4 variables at the same time and having no consistency in the evaluation, because then you don't really know where the improvement is coming from. But yeah, that's the key takeaway. That's the main message, that we are able to use these very specific design choices to solve video problems. And then in the paper, we have like more results on or more data sets, more results. The code and everything is available on the GitHub, so feel free to go check it out. Thank you very much.
And now the first winner of the prize.
Let's make noise for the first winner. So the first winner is, let's make some noise. Oh, come on, make some noise. Oh, yeah. Oh, there's some, come on, some noise, guys. Oh, come on. Are you sleepy? Yeah, come on, let's make some noise, guys. I know you're sleepy a little bit, come on. Whoa, the first winner is... Oh. Okay.
So, Yasser Benagmi.
Oh? This is... Okay.
Hi everyone. My name is Yasser Benigmim, and I will present my work, which is free lunch in open vocabulary semantic segmentation. So this is a work I did at INRIA Paris. So basically, CLIP model is a contrastive learning-based model that has a vision encoder, a text encoder. The model has been trained on 400 million images, so it has strong text and image representations shared in the same embedding space. And usually in the literature, people do open vocabulary semantic segmentation with the CLIP model, and it works the following way. We have the image encoder that gets encoded by the vision encoder. The image that gets encoded by the vision encoder. And when it comes to the text, we have the semantic classes, and each semantic class gets put in all the templates. So for the class road, we're going to put a photo of a road, a picture of a road, and so on. And then we average at the embedding level to obtain robust text representations. So this is the default way of working with CLIP. And then after that, we have a cosine similarity to obtain the segmentation maps. But the question we ask is, what if we use only one template, which basically is this. So instead of averaging over the 80 templates, we would like to only use one, and then obtain the results the same way we did, using cosine similarity. But then let's do it 80 times. At each time, I'm going to have a new model where a new template is used alone. So when I do that, and then I obtain my segmentation maps, I would like to see the accuracy of this segmentation map. And basically, it looks like this. The observation we make here is the following. On the x-axis, we have the classes of a dataset, like Cityscapes dataset. On the y-axis, we have the IOU, which is a metric we use to evaluate semantic segmentation models. And as we can see, for each class, using some templates alone helps you to outperform the average classifier. The average classifier here is the black horizontal line. So, from this observation, which is quite surprising, we ask two questions. First, how can I identify these templates using images but without labels? Because here, as you can see, I had access to labels to compute the IOU, but can I find and identify these templates without labels? And then, once I identify these templates, how can I use them to boost open vocabulary semantic segmentation models without doing any training, so no backpropagation? In order to do so, we do the... So basically, that's what we do. We again come back to this only template we get our segmentation maps, and we're going to use entropy as a metric, as a proxy for accuracy. We assume that CLIP is a fairly calibrated model, which means that when the entropy is low, the confidence of the model is really high, and then probably the predictions are good. And that's what we will do. So we're going to compute here what we call a class-specific entropy, meaning that once we get our segmentation models, I'm going to collect all the pixels that have been predicted as a given class, and then do the average of this self-entropy, minus p log p. And I do that for all the classes. So this is for template number 1. And then I repeat this process for all the templates. Once I do that for all the templates, I get a matrix, basically, where the columns are the templates, the rows are the classes. And now I would like to find my templates. So for each class, I'm going to take only top N templates that have the lowest entropy. And then I'm going to do that for all my classes. So now I have the templates that are suitable to get good predictions on a given class. And after that, I will construct what I call class experts. So what are the class experts? A class expert, basically, if we take the example of the class road, basically it is just the average, just like we do, but instead of averaging over the 80 templates, which are the classical templates that are used from the beginning, from the original clip, we're going to use only 3 templates, the one that I found using entropy. I'm going to average then at the embedding level, as you can see, and then I'm going to obtain my segmentation maps. So now I will repeat this process for all the classes I have. So I will have as many experts as classes. And then, once I get my input image, I will make it go through all my experts. Again, like I said, I have as many experts as classes, so I get as many segmentation maps as classes. In each map, one class is well segmented, not all the classes, only one. And then at the end, I need to merge these segmentation maps, like I said. So how can I merge the segmentation maps? Now, this is my final segmentation map that you see in the middle. So for this pixel x1, which class do I assign to it? I have different experts. Each one is making a prediction. One way to go through this is to do maybe averaging, to do majority voting across the experts. But what we do is something slightly different, which is the following. We have the expert S3 and S4 that didn't make a prediction on their own class of expertise. As you can see, the expert 3 said it's class 4. The expert 4 said it's class 2. So I don't trust them. I'm going to discard the expert. And I'm going to keep only the first 2 ones that made a prediction on their class of expertise. Then I have a conflict between 2 experts, but I choose the one with the highest softmax probability. That's why the pixel is red. So expert number 2 wins in this case. In other cases, I have cases where no expert makes a prediction on their class of expertise. In this case, I can't trust nobody, so I use the fallback, which is the default clip. So now for the results, we have good results across different classes. Datasets, from cityscapes with 19 classes to Coco stuff with 170. So this observation that we saw in the beginning is something that holds across many classes. We have also, as you can see here, with few images, we can compute a reliable entropy. So the black horizontal line is the baseline. And as we can see, with 1 image from cityscapes, we can already have a reliable entropy computation across many classes. Here we show the oracle, which is the upper bound. The oracle is actually the real true template. So when we have the real true template, this is the relative entropy on the y-axis. We see that we can always improve on all the classes once we find the real true templates. And as a takeaway, I would say that clip is really sensitive to the text templates, so use that as an advantage instead, to improve the results. The second thing is that few images are enough for you, like few unlabeled images are enough to detect the class experts. But one last thing to take into account is the inference, which actually grows with the number of classes. Like we said, the more classes we have, the more experts, and therefore the inference starts to grow as well. So that's one limitation of our paper. And at the end, I would like to thank my collaborators that helped me during this internship, and also thank you for your attention.